I will.
Uh,
How you doing?
I'm sitting on the project right now. Just I don't know. I got AN is 118.5 meters per second squared. Sounds like a lot, no?
Let's see. Look at that. For at X is 10.
Yes.
Yeah, that's right.
Oh, that's right.
Yeah,
And the angle is 12.95.
that's right. Mhm.
Okay, good.
Basically, with that AN, because you're at the bottom of the pipe where it's turning really sharp, does it make sense? It's redirecting you super hard. Remember that you want to go
Oh
straight,
yeah. Mm-hmm.
and it's saying no. It's super
Yeah.
sharp. So again, that number is hard to make sense of, but it's basically a lot of force of redirection right there is what it comes down to. When you get up to the point X is 14, now it's kind of flatter. It's not redirecting you much. And so your AN should be a
The
lot
number is
smaller.
gonna be smaller. Yeah.
Mhm.
And okay, when I'm gonna go to x equals 14, do I still have to measure it from 24?
Yeah. Now you could go from 10 to 14. You can go from any place you want, but because at 0.24, your speed was 0, it's easier to just go from there to
Mm-hmm.
14. Now you're higher in the air. So does it make sense your velocity is now less because you've traveled back uphill and lost some velocity? So you should get a smaller velocity answer for 14 than you should for 10.
Mm-hmm. Yeah. And our AT at x equals 10 is that should be negative, right? I didn't solve it yet, but is that should be negative?
That's right. Because you're going up a hill, therefore you're slowing down.
Mm-hmm.
Both cases, you're actually traveling up a hill. One place is steeper than the other. So the steeper one should be slowing you down more.
Mm-hmm. Okay. And I'm assuming we're gonna have a question like that on a test, right?
Mm-hmm.
Okay.
Yeah.
And you said test is gonna be tomorrow?
Yep.
Um, well,
Anytime
I
you want
think
tomorrow, basically.
okay. I think it's better still to wait for everyone to talk about the test.
Yeah. Yeah. Keep asking me questions about the project if you want.
Okay. Let's see. The question is, so when I got this 12.95 angle, we're measuring it from the level, right?
Exactly. It's always from horizontal.
Mm-hmm.
So notice
But
that looks right, because if you take off from the point 10 to horizontal, you're not angled up very much. You're not climbing very steeply. So you should get a much bigger answer when you're at 14, right?
yeah. Okay. I mean, this question is actually not that bad. This one, plus when you open up the video, I watched it, like the end of it, and it explained a lot of stuff for me. I was just not really sure because when me and Ben usually was doing projects together, we can compare the numbers we got, which
Absolutely.
is like if you got two the same numbers, it means it's pretty close to 100% being correct.
Yeah, that's right. Well, and that's actually one of my concerns about this project, because the one that we started the other day, I mean, I said it's just due before you take the test, but I really would like you to know you're getting it right. Like,
Mm-hmm.
I'd be unfortunate to not be getting it right and then take the test.
Yeah. So if I got correct angle, I can find the gravity now. Parts.
Why don't you keep working on that for a few minutes while we're waiting? I don't know what we're doing. Maybe it's only you and me, but I would like to give you a few minutes so actually you can at least leave today knowing you're doing it right. Like if you can check all your answers for at least 10, then you'll know 14's right.
Yeah, 14 is pretty much the same thing. It's just
Yeah.
because it still goes up.
Yeah.
So it's the same thing.
Well, the main reason I had you do 2 different points is not just to practice, but so you could compare numbers like, hey, why is acceleration tangent at 10 one number, and then acceleration at 14 it's a different number? You know, why is one bigger than the other? That should actually grow your intuition for physics as to, yeah, like of course that would be the case, you know, that kind of thing.
Yeah, like on example you gave us at the class was a parabola on it. Like we got a negative angle on it.
Right.
Yeah, which just makes sense. It's you're going down a hill.
That's exactly right.
And the same negative slope shows that too.
Yep, that's exactly right.
Okay.
So what are you going to do to get acceleration tangent, or what are you working on right now?
So I'm gonna find the components of the gravity force.
Good job. Yeah.
Yeah, and after that, find the tangent and normal. Not normal, right?
Yeah. Yeah. Do that right now. That'd be good. I'd like you to
Okay.
check your work on that.
So because our tangent always, I think you told us that tangent and normal, that's our positive directions, right?
That's right. So the positive tangent is in the direction that you're traveling. And notice,
in the direction you're traveling. Okay.
yeah,
That's
normal
negative.
is always toward the center of the circle that you're traveling on.
Okay.
Notice at 14, that's actually kind of hard to tell. Like if you're clear up at 20, does it make sense that positive normal would be down because the circle is pointing down?
Yeah, that one is actually really difficult to tell, but it's not on the middle, right? Like that
No.
14 point, it's not on right on the middle.
No.
But if the point is going to be right on the middle, how are you going to find that?
Yeah, but interestingly, the radius is infinity. And that happens because the second derivative on the bottom is equal to 0. Because there is no change at that point. And so you'd actually have an infinite radius if you're right at the transition point, which is kind of weird to think about.
So if it's so our AN is going to be infinite as well.
Anything about that?
Or like super small.
Yeah, it should be super small because there is no desire to change direction there. So A of n would be 0 if you're at that point. If you're close to that, like we are here, then you're going to be close to 0. Like you'll have a really small number. It's not going to be like 118 like the other one. It's going to be much smaller.
Okay.
And that's basically if you have velocity squared divided by the radius, but the radius is infinitely large, then velocity squared divided by infinity will be on its way to nothing. So that acceleration normal will be on its way to nothing, which makes sense because you're not being asked to change direction based on the curvature. That makes sense.
So tangent is equal negative 9.6.
Acceleration tangent?
Yeah.
No, what did you get for your the component?
Oh wait, I used the wrong number. I'm sorry, I used the wrong number. I used 152.97. I should use the 35.17, I think.
You're right.
Here we go. Negative 2.2.
That's right.
Okay.
So notice that's a pretty small number because down there where it's flat, gravity is not, it's not really steep. So you're not like, if you're climbing something really steep, you'd be slowing down really fast, but because it's kind of levelish down there, it's not really slowing you down much, but you have started to climb. So it slows you down a little bit. If you're right at the bottom of that, then the acceleration would be nothing because you're in the flats right now, at least for that moment.
But if you have all of your, okay, you have all of your acceleration generated by going down a hill and you coming to like way bottom of this, the valley basically. So at the point, it's not a 10.2, right? Yeah. I don't know what's the bottom point on it. It says acceleration is going to be 0.
That's right.
Okay.
Because gravity, all of your gravity is going down and none of it's going left or right. So you have no force pushing you anywhere because you're not on a hill, basically.
Oh, okay. Yeah, makes sense. For normal force, I got like 2K. Is that right?
Yeah.
That's a lot. Everything else.
I'm going to share a screen. I want to show you something.
Mhm.
I made a Desmos to kind of model this. So take a look at this. Like here's the skier skiing along, and I basically have all of these updating automatically. So this is the same order as on your sheet. So that's the angle. Well, look at this. Look down here at this normal force, what you just calculated. So see how where I am right now, that answer is only, oh, if that go away. That answer is only like 71. Now it's like 43. Remember what that means is what that means is how hard is the snow having to push on you perpendicular to keep you there, as well as change your direction. Well, would you agree up there you're basically going really close to straight? So it isn't having to, the snow isn't having to push against you very hard to change your direction up there. But when you get down here, isn't it having to push really hard on you to get you to change direction? So notice how huge that number is, because it's pushing really hard on you. And notice it's kind of weird because it's way bigger than just your force overall. If you take your 16 kilogram mass times roughly 10 meters per second, so mass times acceleration, that's only 160 newtons. If you're just sitting on the snow, it'd be 160 newtons of force straight down. But because the terrain is turning, this is like riding a roller coaster, it's pushing super hard against you to change directions down there. So down here at the bottom is like the biggest number you'll get. And then again, I'm looking at this NS number over here. Notice that number gets smaller and smaller and smaller up here because again, you're going straight again. So it's when it gets into these corners, see how it increases again? It's pushing really hard on you again because it's trying to get you to change direction. Notice in this case, it's negative because it's actually pushing down on you. So yeah, that's why that number is so big. So 2045, somewhere in there, like that's the number you just got. If you're at that point right there, it's pushing really hard on you, but even harder if you go to the bottom, which looks to be about when X is 9, but I don't know if that's exactly right or not. Do you see logic in that?
Mm-hmm. Yeah, it's just when you're coming to like when X equals 20 on that spot out there, because there's nothing is going to push down on you, only the gravity, but it's probably going to be not enough, so you may be going to fly.
Well, think of this as like a roller coaster. Pretend you're upside down and you're
Mhm.
going around that corner. If you're upside down, like you would just fly through the air. Like if this was a skier, you actually might fly through the air and release. So interestingly, what it kind of depends on how you look at it. Watch that number right there. So let's think of it as a skier on the snow. So now it's 133 and then it's 120 and then boom, all of a sudden it's negative. What that means is the snow is not pushing on you anymore, which means you've left the slope. You're flying right now. So when that N of S is 0, that's the moment that it's not pushing on you at all, which means you've now started flying. So at this point right here where I'm at 17, you're not on there snow anymore. You're actually above it, flying through the air. You're gonna fly, like if this was the ramp, you actually would stop following it and then you'd be like on a parabola flying, like this and landing way out here somewhere and dying or whatever. So negative normal forces against you when you're driving means you're jumping, or when you're skiing means you're jumping. It's kind of cool. You see
Makes
logic
sense.
in that?
Yep.
Take another couple minutes and then we'll start on the slide project, which will help you for the test. So
I mean, I'm done with the half of this project, so
Okay.
After the class, I can finish the other half.
Okay, let's start that now. So you can see this yourself in my open math, but I'm going to share a screen. So today's project is, again, very tangible, very practical. We've talked about a problem exactly like this, but entirely theoretically, where a skier slid down a hill. So skier got up here, slid down a hill, got to the end, and then flew off and landed on the ground. We did a problem just like that, except for it was all very sterile. Well, this is not going to be sterile in the sense that we're actually going to slide a box and so forth, and we're going to try to actually predict it. So the powerful things here are in the problems that I gave you in the past, and typical book problems, you're given coefficients of friction, and you're given weights and all these things. Well, we're just going to go measure all that stuff ourselves. So one thing, let's just play with this for a little bit over here so you can see it. I'm gonna. So in the end, what we're going to do is try to come up with our own coefficient of friction, come up with our own weight, and then slide the box from the top and then just kind of predict where it's actually going to land and see if we can do it. Like, see if we can figure out everything ourselves, take our own measurements in kind of an old school sort of a way. So I'm going to put up the second camera view. So I went out in my garage and grabbed this bench that I made to put shoes on. So that's going to be the ramp. And for a second, I just want to play around with a couple of things. See, I got to turn this so I can see what you see. So I just grabbed a box here that I found in my garage that's got an inner tube in it. What's your thoughts? Do you think when I put it on that ramp, it's steep enough that it will slide?
That's actually really difficult to tell. I mean, maybe.
Yeah, and you should have no way of answering that question. Don't get me wrong.
Well, sometimes if the angle is really steep, it's easy to say yes, but this angle here, it's difficult to say.
Yeah, that's exactly right. So here's a trick question. It's not sliding.
You got a rubber on it.
Not only that, it's still not sliding. Are you surprised?
You got a rubber on it.
Exactly. I put rubber bands around it, and watch this. This is kind of cool. Notice if I tip it up, it doesn't slide. And at some point, I don't know if it'll stay there, but at some point it actually just tips over. Does it make sense? It's so sticky that it won't slide, but the center of mass of this, as soon as the center of mass gets out beyond the front of the box there, then it just tips over. That's kind of weird. That's kind of interesting. So, of course, by putting that rubber on there, this is why our cars and roads are this way. I created a ton of friction that if I take those off, then it might start sliding. So notice that sliding, and it actually kind of feels pretty good that it is sliding. Now, one of the things that's going to be difficult here is how even is this surface right here? Does it make sense if it hits any kind of a, like an imperfection, maybe there's like a little rock in it or something. If it hits any of that, it's going to screw all this up, right? One thing I think I could do to make that work a little better is make it a little steeper so that it slides a little more obviously. Does it make sense if it's barely sliding, then the slightest imperfection would kind of screw it up? Do you understand that?
Yep.
So I'm going to tip it up a little steeper so that when I put it on here, it just starts going immediately. That feels pretty good, don't you think?
Yeah.
So we need to know quite a few things about this. I guess I won't, maybe I will show you this. Yeah, I think I will. One of the things we need to know, you're going to get dizzy here for a second, is the weight. And I brought a new scale from school, and I noticed it doesn't weigh the same as the other one we had, so that's kind of sad. So here's the weight of the box. So make a note of that, 206 grams, that's how much that's the mass of it. Why do we care about the mass?
The later on, we're gonna calculate the forces.
Yeah, that's exactly right. And remember, if it's really heavy, then friction will sort of have a bigger effect. Does that make sense? Like it's pushing harder into the ground, if you will.
But at the same time, the surface area, no?
That's a good question. And if we were trying to calculate it based on, because you can kind of calculate, you can look things up online and figure out how much, what is the friction coefficient, and you can kind of look that kind of stuff up, and then maybe surface area would matter. But we're actually just we're gonna get this entirely by measurement in kind of a much neater way. So if you have your cell phone nearby, can you find a timer on it?
Sure.
So then I'll give you, I'm gonna probably do this with you. Let's see, so we got a mass of, what was it, 206 grams?
Yep.
So we know it's mass. And what I'm interested in is if we bust out our cell phones, get a timer, and we time how fast it's going to take to go down, the question is, could we use that to figure out what the coefficient of friction would be? And the answer to that is yes, but I'm going to kind of let you, I don't know if the right word is struggle a little bit, but and I want to show you one other thing first here too. So on my phone, I remember if I had occasion to show you this before. I have an app on my phone that will actually tell me the level of what angle something is at. So, as I'm looking at that thing over there, it makes sense. We need to know what level it's at. Notice I'm holding my phone roughly level, and you see how it's reading 90 degrees?
Mhm.
So it's calling that level. So let's see if I go over here, I'm hoping you can see this at least a little bit. And I just adjusted it with a few books here, but I can't tell. Can you see that? Because I can't hold this and look at my cords. Is
70.4, is that what it is?
Yeah, it reads 70.4. Let me slide it around a little bit just to see if it's different any other places. I got 7.5 down there. 70.8 down there. 70.2. Let's call it 70.6. Now, remember what that is off of 90. So 70.6 off of 90, that's actually 19.4. That thing's at a 19-degree angle. Is that right? 19 plus 70. Yeah, 19.4. You understand that?
Yep.
So our ramp is 19.4 to the ground. Okay, cool. Now, what we'd like to know is how long does it take to slide to the bottom of that ramp? And to be very careful, does it make sense? I kind of need to slide it on the same side of the box every time because there could be something weird. So I'm going to slide it with that white side kind of down every time. And I'm going to try to be really consistent. And I think what I'll do, like, so that we can both kind of time it together, is I'm going to go 3, 2, 1, start. And like, that's when I'm going to let go.
Okay.
And then where we're going to screw up is, when does it leave the ramp at the bottom? So that's going to be kind of guesswork. And of course, it'd be wonderful, if you will, if we had the physics equipment to, somehow like have beams that it would break and, get it perfect. But who really cares? Like the whole goal here is just to kind of reason this out and, even if we had a time that was totally wrong, but we'll be reasonably close. So what I'm going to do is say 3, 2, 1, and I'm going to hit start. right when I say start. 3, 2, 1, start. And then where do you think we need to, the problem is the box is really long. Does that make sense? So do we do it right there? Like if we have a choice, we want to do it like right in the middle or right when it gets there?
Depends where you're gonna take the measurement from, the distance.
Yeah. I mean, I think we need to consider the box as like a particle, in other words, the center, right? So if I start it with the edge of the box at the top right here, then we're actually thinking of it as starting about here. Do you agree with that?
Yeah.
Middle?
Mhm.
And so I think we should think middle to middle. So let's try to stop it when it goes off the end. Now, again, we're gonna do a terrible job at this, right? So even talking about that, it might be kind of stupid, but let's just see how consistent we can get. Because to me, this is a fun part of the science of this is, if we don't want to just do one trial with one phone and then go on. As far as the math is concerned, that'd be fine. But just out of curiosity, I wonder how accurate we can get by just playing around with this. All right, let's try one. Ready? 3, 2, 1, start. That's hard. What'd you get?
I got 1.52, but I think probably more like 1.4.
That's exactly what I got, 1.4. You felt like, because that's one of the things that's interesting about this is some of those times you're gonna feel like, oh, I stopped it too late. So again, one of the cool parts of this is to kind of think about statistics. If we were gonna do this really well, we might do it, say, 5 times. And it'd be cool, like we're doing, to have more than one person, and then to say maybe throw out your lowest time and your highest time, and then average the remaining ones. And it'd be interesting to see if, like my average was different than your average, because I'm like trigger happy and stop mine too soon every time, and whereas you're like slow and stop it too late every time or something. And then we can decide
how we can do this other way. The iPhone have a slow motion camera. So you can start recording, and after you're just gonna, scroll.
Yeah.
Stop at exactly when it's gonna hit the point, the middle.
Yeah, that's interesting.
Yeah, and you're gonna know almost exact time, like super close.
Is that what slow-mo is?
Slow motion, you can just go to the camera, and you can just record the video in the slow motion.
But you do it in slow-mo mode, right?
Yeah. Yep. Mm-hmm.
So you're thinking we could get away with just recording this and then
yeah, and after subtract, see when you actually drop the box, and it starts sliding, and look on the timeline when that happened, and see when the center of the box passed the edge of the table, right? Because you can see it easily. It's in a slow motion.
Yeah, that's a good idea.
And I think that's how they usually doing it. That's how they timing all their like whatever stuff they timing.
So yeah, and of course I would need to have kind of a third person here or second person to kind of hold this, and because you're saying you could turn it on early, you don't even have to turn it on at the same time. You could just turn it on early and then watch your finger go up and then see what time that is, and then say slow mo at the bottom.
Yep.
So that's kind of cool. Let's try it. I'll try that. I wonder if I'll be able to see the end of it very well. I wonder if I step back while it's happening, if it's fun. Let's just play, man. See what this is all about. All right, so I'm saying go. No, it's not very accurate. It's only showing, when you break it down, does it go to, it's showing like 1 second, 2 seconds. Does it break it down so that you can see hundredths of a second?
I think so. I think on my phone it can do that. I'm not sure about your phone, but I think my phone can do that.
I'm gonna try it once and just see. Okay, get on. Timer is happening. It slides. Stop. Now I go back. Looking at the time lapse. God, that is really slow motion. That is rad.
Yep, and you can scroll to the actual the time when it left the table.
I think it is working, so take a look at my camera. Just in the interest of time, let's go ahead and use this because it may be pretty accurate. So
So
you can't really see that because of the zoom feature. You see how sometimes like right at the bottom, it's saying point, it's saying 10 right now.
mhm.
So now it switches to like right there is where I'm lifting it, which says point, which says 1-1.
1-1.
Yeah, so it says 1-1. Whoa, come back. God, that is so fun.
Yeah, you see that? That is pretty accurate, I think. I mean, you can see it.
Yeah. It says 2-2, 1-1 to 2-2. So does that mean, what's that measurement? Does that mean 1.1 then?
I think so. It's like a 1 point. Yep. Let's see. 2.
It was like 1 second.
So that it took 1 second.
So according to this, it says 0-0 colon and then 1-1 when I let go. And then it says 2-2 when it gets to the halfway point. So the question is, what does colon 1-1 mean? Does that mean?
The other thing what you can do, you see the edit button on the bottom of the screen. Now you can cut the video to exactly when you let go of the box, and I think it's gonna be a little bit better. The exact moment. And after, when you're gonna save that video, just try to save as a new video, not try to replace the original.
Mm-hmm. Pretty close. Yeah, I mean, it doesn't really, still says colon 1-1. So the question is that 11/60ths? Or does it literally mean 1.1 seconds?
I mean, 1.1 seconds sounds right, because we got when we timed it, we got like 1.4.
Yeah, 1.4.
I think so. We got 1.4. Let me double check. Yeah, we got 1 point. I got 1.52, but I think because of a video delay and all of that, I think it's like 1.4.
Yeah, okay, well, in the interest of time, let's shoot to that. So let's just call it 1.4. So time 1.4 seconds. So what I want to know is, based on those things, could you calculate what mu, the normal, I'm sorry, the coefficient of friction would be? I want you to think about that because I don't think that's obvious at all. But start out by drawing a free body diagram. Like don't think so much like step 1, step 2. Just think, I'm going to draw the picture of the sort of the skier there at the top of the hill. Think about all the formulas that you know.
So we pretty much got normal force, gravity, and friction, right? Acting on the box.
Yep, that's exactly right. And the 19 degrees has converted some of our gravitational force to
Yep.
downward motion.
Mm. Are you solving that as well?
Yeah,
Okay.
I'm just figuring things out. That's very important because I'm not immediately, if you will, knowing exactly like what do I do to find mu. I'm just kind of starting with all the formulas that I know. I'm drawing a free body diagram of it.
So I found that let's see, the gravity that pulls the box down, it's a 2 newtons. Is that what?
Yep. Yep, that's exactly right. I kept it more accurate, called it 2.021, but that's kind of dumb because it's not going to be that accurate.
Okay.
Notice this isn't curved motion, so we don't have to think about rho and all those kinds of things. It's straight line motion.
Mhm. You got a gravity normal force yet?
Yep. What'd you get?
1.9.
Yep.
Okay. And 0.67.
Yep.
Okay.
Nice job.
There we go. So because our velocity was starting at 0, right?
That's right.
And acceleration and time, we do know time.
Yeah, so we have a time. So how are we gonna get that involved?
So what is that?
So from the center of the box, it's 47 3/4. That's how far the center of the box slid. That's inches though, because that's the only measuring device I have. So
Okay, let me convert it real quick.
blur out anything you want while you're working here, because I can answer it.
Okay, so you said 47.75, right? 3/4.
Yep.
So into centimeters, it's 121.28 centimeters.
That's exactly right.
And we have to convert that to meters, right?
Very well done. That's exactly right as
Okay.
well.
Okay. 1.21.
Yep.
Okay. Got a distance of travel. Is that distance times the time? Is that what it is?
No, you need to think in terms of the position equation,
Or the position?
because the velocity is increasing the whole time. So that's the problem. We don't know the velocity. We
Oh,
know
yeah.
it at 0, but
We still have to know acceleration, right?
that's right.
So we can put our total distance into S, right?
That's right.
And we can find acceleration after that.
That's exactly right.
Okay. You got 1.23?
Yep.
One, two. Is your next step as velocity?
My next one, I don't think there's anything wrong with that. I was trying to figure out the force of friction next, using the sum of the forces. Sum of the forces in X equals mass times acceleration in X, now that I know that.
Mm-hmm. Okay. Getting a little bit confused about that sum of forces in X. If you're making the table as pretending as its level, then our negative F friction, force friction, is going the opposite. I mean, going the opposite direction of the travel.
That's right.
And we adding the tangent gravity force.
What is your Yeah, tell me what your sum of the forces in X equals mass times acceleration in X. Tell me what that equation looks like.
Let's see, mass times acceleration. I think I mass times acceleration. Here we go. I think I didn't do that yet. We're talking about the 9.81. Is that? Or are you talking about the acceleration we just found?
The acceleration we just found, because the acceleration, I'm thinking of X as the, like the plane is kind of our X axis, that angled plane is our X axis. So now that we know that it's accelerating down that ramp, thanks to the time that we had,
So you said mass times the acceleration.
should equal the sum of all the forces in X.
Oh, okay, okay, yeah, okay. I got negative 0.42.
For mu, what's that? You got that for what?
This is, I mean, I did a sum of forces on X equals mass times the acceleration.
Got it. So that's the force of friction. Got it.
Yeah.
Yep, that's right. Now, what is the normal? What's the normal force that the wood is providing to the box?
Okay, normal force. Now we're just gonna do some of the forces in Y, right?
That's right.
But there's no acceleration, right?
That's correct, because it's not moving. That's
Mhm.
exactly right.
You got 2.11 for normal force.
No, what equation did you set up?
Normal force minus 1.9
Correct, equals what?
Equals 0, right?
That's right, because it's not moving.
Oh shoot! Yeah, okay. Yeah, I got it. So it's just 1.9.
That's right.
Okay.
And you're exactly right. That's because the acceleration in the Y direction is nothing. thanks to the fact that the wood is there holding it, not letting it go in the Y direction.
And what is the question again? How far is it gonna fall off of the desk?
Yeah. In other words, where is it going to land?
Mm-hmm.
And armed with everything we know now. So number one, it's kind of cool that you can actually figure out the mu just based on all the time and so forth we have. Because does it make sense that the force of friction is equal to that normal force 1.906 or 91 times mu? So therefore we can now figure out what that is.
Mm-hmm. I got 0.22.
Yep, that's what I got. So it's kind of surprising, if you will, how many calculations it takes to actually produce that friction number,
Mm-hmm.
which is kind of cool. Interestingly, though, in a sense, we don't need it because we had time instead. Like all the sort of book problems give us mu, and then that allows us to figure the time out. But in the real world, that'd be hard to know. So we were able to measure time. Therefore, we figured out mu. So that's just kind of cool to know. But we actually, time is a better thing to know than mu, because if we know how long it takes to get to the end, we just sort of know everything we need. The only thing we actually really need to know to proceed is how fast are we going when we get to B, the bottom. In other words, the bottom of the table. I labeled the top A and the bottom B, kind of like the picture that I sent you in my open math. Question is, what do you do to figure out the speed at B?
Okay, speed at B. So I plugged the acceleration times the time, and I got the speed 1.722.
Nice job. That's exactly
And that's should be at B, right?
Yep. So that's
Yeah.
the speed where it leaves, and we know what angle it was at when it left.
Mm-hmm.
So we should know everything we need to figure out how far we think that thing's going to fly through the air. So the cool thing is now there's no table there anymore. So therefore, there is an acceleration in Y and there is no normal force anymore. Nothing's pushing on it anymore. So that's kind of the realm change.
Mm-hmm.
So it has an initial horizontal and an initial vertical velocity now.
What do you got?
13 3/4.
Okay, so it's 0.34925. You got velocity in x 1.62.
Yep.
And in y it's 0.57.
Yep. That's what I got. me go grab a tool I know we need.
Sure. Can I ask a quick question?
Yeah, go ahead.
Do you got a time already?
Yes.
Is that 0.35?
I got less than that. What did you do?
Let's see, what did I did? I got a negative acceleration time squared minus 0.57 times time and plus the distance from the table to the ground.
That's right.
And I graphed it, and
Did you have a 1/2 in front of that acceleration?
yes.
So yeah, I did quadratic formula. I have.
Did you got maybe 0.21?
That's what I got.
Okay.
One of your times should have came out negative, which is not the right one.
Yeah.
Right back.
Okay.
I'm gonna use this level. Do you understand why?
Yes. To find the distance a little bit closer, you're gonna measure it from that spot. Let's
Yeah.
see.
So the question is, what do you think that distance is?
I think what I got is gonna be 13.4 inches.
That's pretty good. I got more like 13.8 because I rounded a lot less than you did. But considering all the variability in all of this, I'd say that's pretty good. What's your thoughts on that?
From this angle, it looks maybe a little bit too close, but
That's
it's just from
interesting.
this angle.
I was thinking from what I'm seeing, it actually looks too far.
Oh, now, yeah, it looks. Looks not bad, actually. I think it looks not bad.
Yeah, so one of my concerns about all this is we're hanging everything we just did on 1.4 seconds. And that number is probably not terribly accurate. I put that eraser basically in the middle of what I got, which is 13 3/4. You got 13.4. 0.4 would be 3/8. So we're only different by 3/8 of an inch. So that eraser gives us a little bit of room for error. So what I'm going to attempt to do is film this in slow-mo.
Yep.
And hopefully we'll watch it just bump that eraser. Yeah. Let's see here. Here we go. Boom. Pretty rad, right?
Oh, I'm happy.
Okay. Now we got to scope this out in slow-mo. Because we got to see. Can you see that okay?
Yeah.
So we do have to think center of mass. So that's a little hard to tell where that is exactly, but. Bam.
I think it's really accurate.
Yeah, because I'm thinking this, the center of it is not the middle of the box, it's actually the bottom, since that's what was sliding. You got to think about that a little bit. And it landed right in the middle of that eraser, though. That's pretty rad, wouldn't you say?
Yeah. And after, can you send me this this video? Just text me this video, I guess.
Yeah.
This is insane.
I did not crop it yet, but yeah, show that to your mom, pa.
Yeah.
Fun.
Insane. And there's after like a page of the calculations.
Isn't that crazy though? I mean, this is kind of cool to watch it work. Don't you find that that's why I think this is such an important project to me, because it increases your kind of your confidence in what all of this is doing, and it makes you think about it more deeply, given that you're kind of stuck with not so much information. Like we had nothing but tape measures and scales there to predict all of that, which is so cool. Yeah.
Let me see.
I'm gonna go in and do what you said, which is edit this. Should have sent you the edited version.
It's okay. I mean, I can cut it. That's all. Do you want me email you the project like this one we just did?
No, we did it together and you verified all your answers with me. So let's not say we did. I don't see any reason why we need to do that. Hey dear, Evelyn and I just succeeded in landing an inner tube box onto an eraser. Yeah. She's not as impressed as we are. Maybe I didn't explain it right, Evelyn.
Probably.
I'll put you on speaker. Yeah. So,
I'm very impressed with your guys' endeavor today.
yeah, I got paid money and Evel got a degree in civil engineering today, and that's what we did.
Nice, nice.
So let me say something to Evald here, and then then I'll talk to you. So Evald, if you want to send me like a picture of your 14 on that other prep for the test thing, I'm not worried about it because you got the first part right, and the test will kind of be more like that. The test is going to be a more simplified version of that, but I'll open up the test tomorrow, anytime after 8 o'clock. So you can basically take it anytime tomorrow and send it to me. But if you want to, send me any of that or whatever, just out of your curiosity before you take it, like later today, you're certainly welcome to.
Send you the